as of today, ChatGPT can sort of get computational superpowers by calling on Wolfram Alpha and Wolfram language through its plugin mechanism. And ChatGPT is a large language model which has kind of gone through the web and lots of books and so on, and it is piecing together things by sort of seeing what a reasonable piece of continuing text would be. And it's amazing how far that gets. And we'll perhaps talk a little bit later about why I think it gets as far as it does. But the thing it isn't able to do is actually do sort of serious computation. It is just saying, let me continue this text based on things that I've seen on the web and things that sort of seem reasonable based on the structure of language as humans have written it. But when it comes to actually computing things, that's just not something a neural net like it does. But we've been building for a long time now, Wolfram language, we'll talk about that probably a bunch later, our sort of computational language to represent the world in a sort of precise computational way, and Wolfram Alpha, the kind of consumer version of that takes natural language input, converts that to Wolfram language, to precise computational language, and then does computations. And very conveniently, ChatGPT, in a sense, talks natural language too, so that provides a kind of immediate bridge through the Wolfram Alpha natural language understanding system so that ChatGPT, when it wants to actually do a serious computation, can now reach out through Wolfram Alpha or directly to Wolfram language to our whole technology stack to get those computations done. And obviously another piece of what we've done is to get sort of computable curated data about the world and sort of implement the models and methods and algorithms and so on that are needed to sort of compute expert level answers to things. And so now ChatGPT has access to all of those kinds of tools. I think it's kind of an exciting moment in kind of a merger of two different sort of approaches to kind of the problem of AI, the sort of statistical approach of just sort of see what's out there and kind of learn from that, and the kind of symbolic approach of see what you can actually compute. I would say that the things we've done, haven't really viewed as being, quotes, AI as such. It's more the deeper story of computation. But now we've got this kind of merger of these two approaches that just released about an hour ago now.
Yeah, it's amazing. I don't think anyone would have seen this coming, even 5 years ago when language models started coming onto the scene, that they might be used as a tool to take a natural language intelligible input and transform it into a representation that can be used on a downstream system. It's absolutely amazing. But why don't we go on a bit of an intellectual journey? Because I was very interested reading your book, and I wondered whether you could, we'll just start with how the language models work and kind of build from there. Philosophically, and I mean philosophically and deeply, because our audience are actually experts on deep learning. I wondered if you could talk about how language models work from your kind of abstract, deep understanding, what the reasons are for their success. And you said in the book that computing the probability of even 10 tuples of language would require more data than there are atoms in the universe, which is very interesting. So language models are clearly doing some kind of clever interpolation. And most importantly, the thing that I'm very interested in is, what does it mean to understand? Do you think that our language encodes enough representational fidelity to afford a useful semantic mapping to grounded reality, or to what most people would understand in the world? And I'm sure you're aware of two major strands of thought in the philosophy of meaning, which is to say meaning as reference and meaning as use. So perhaps you could bring that into your answer as well.
Well, okay. So what does it mean to understand something? One of the things when we built Wolfram Alpha in 2009, people have been trying to make, natural language understanding systems for a long time. The problem that they always had, which I didn't realize until after the fact, I have to say, was that it wasn't clear what to understand actually means. You have this computer, it's doing what it's doing, but what does it mean to understand? Well, we had a very definite definition of understanding. It was take the natural language and convert it to our computational language from which a computation can be done. We had a target for understanding. We had something which was kind of the ultimate representation from which we could do all these things with computation and so on. And that was our operational definition of understanding. Now, when you ask a question like, I think it becomes a much muddier question when you say, what does a language model understand? For me, sort of the gold standard of understanding is you can convert it to a computational language, you can compute all sorts of things about it, you can kind of you can figure out from it anything that can be figured out from that from that sort of thing that is represented in this precise way as computational language. I think the thing that I've sort of realized, so I've been interested for a long time in kind of how do you represent things in the world in a sort of formal computational way. That's been the whole story of building our Wolfram language computational language. But I've also been sort of interested, I've been curious for a long time, how do you take kind of everyday discourse and convert it also to something computational? You know, in Wolfram language, for example, let's say I say, I want to eat a piece of chocolate. Okay, in Wolfram language, we have a lovely representation of pieces of chocolate. We know about all kinds of different kinds of chocolate. We can characterize the size, et cetera, et cetera, et cetera. We haven't had a characterization of the I want to eat part of that sentence. But it is something I've long thought should be possible to represent in a kind of formal computational way. I think what ChatGPT is showing us is that, yes, it really is possible to think about language in kind of and the things we represent by language in a quite structured way. So, I mean, the way I like to see it is what ChatGPT has discovered regularities in language. So first thing, just to comment on this question of, you know, when it wants to make a continuation of a piece of text, you know, if it's just a single word, it might be able to go out on the web and just look at the corpus and figure out the probability based on other occurrences of the previous words. But by the time, as you were mentioning, by the time it's any substantial number of words, there's no way it can have sort of, you know, statistical data to just work out the probability from that. So it has to have a model. And one thing that's really interesting about neural nets is when you have a model, there's no obvious definition of a right answer. You know, there could be, but our operational definition of a right answer is it sounds right to a human. So the thing that's really interesting about neural nets is they do this modeling, they do this continuation, they do this extension beyond the merely statistical, so to speak, in a way that corresponds to what we humans expect. Perhaps that isn't surprising because neural nets are architecturally quite similar to brains. And, you know, neural nets, as they exist in ChatGPT, are remarkably similar to the kind of original idealization invented by McCulloch and Pitts in the 1940s. But they're kind of the fact that what the continuation, the particular model that ChatGPT or a neural net is using is something that corresponds to what we humans expect. That's the thing that's interesting. You know, if we were to imagine the aliens or the octopuses or whatever else, it's not obvious that the thing that would be a reasonable continuation for us would also be a reasonable continuation for them. But that's a feature that happens to exist, that we've discovered exists for these idealized neural nets that we use in things like ChatGPT. Now, the question then is, well, when we see sort of, what did it discover about language that allows it to make that model? What's in that model? It could be the case that that model is just something that we humans will never understand. It's something that's kind of the insides of an automated theorem proving system, or something that are kind of a lot of structure, or the insides of a machine learning system where we look at it and we say, well, that's interesting, it works nicely, it picked out some features, we don't understand what the features are, it's not something that's beyond sort of human understanding. But it's interesting to try to see, can we get some kind of narrative understanding of what's happening? And I think the two things that we know about language, one is that it has a definite syntactic grammar. You know, we know nouns and verbs go in the places they go. It's one thing we know. The other thing we know is that logic works in language. I mean, when logic was originally invented by Aristotle and so on back in antiquity, you know, that my imagination of what Aristotle did is something much like a machine learning system would do. He looked at lots of examples of rhetoric and he said, what are some patterns of how language works in these pieces of rhetoric that are sort of making arguments and so on? What are the patterns of language that successfully make arguments? And from that he extracted, you know, syllogistic logic, all men are mortal, Socrates is a man, therefore Socrates is immortal type thing, those kinds of structures. He extracted from language this kind of superstructure that is the kind of abstract logic. And from that, much later in the 1800s, you know, Boole and people made it more mathematical, made a kind of tower out of logic that goes beyond what is represented directly in language. But I think what we're seeing in ChatGPT is it's sort of discovered, and we don't yet know what these precise patterns are, but it's discovered kind of a semantic grammar of language. And I think the way we can think about what it's doing is, it is putting together essentially these puzzle pieces just like when you make a syntactic grammar of language, you're defining these are the kind of trees and so on that you can put together. These are the parse trees you can put together to form a syntactically reasonable sentence. Well, it's finding the things that will allow you to put together a semantically reasonable sentence, essay, whatever else. And so I think that's my sort of understanding of what it's doing. Now, if you say, is there an underlying sort of understanding that it has? Again, I consider that a very floppy question. I consider that the really well-grounded version of that question is, can we turn it into something computational from which we can then use a precise formal system to go and figure out things from it?
Or even maybe the next step might be, can we, once we have that structure and we can perform computation on it through Wolfram Alpha, for example, can we then turn around and turn that into action that we can take into the world that has, certain desired effects? And this is why I wanted to ask you is, okay, Bing came along and sort of provided some computation to GPT, but very restricted, restricted to searching and that sort of thing. Wolfram Alpha now finally gives it the power of full, complete, Turing complete, anything goes, kind of calculation. If we now allow it to feed back on itself, so this system, ChatGPT plus Wolfram Alpha, if it's now able to say put information back into the infosphere, send out tweets, put stuff on a web page that can then come back through, the GPT, engine, which, as you say, we may never understand it. It may just always be kind of a black box to us, but it can add its little bit of natural language magic and complete the circle. We now have almost this massive Turing machine that has these hybrid components to it. Is this potentially the first step towards artificial general intelligence, or are there still some missing ingredients?
Well, I think that the picture you paint, one of the points that I think you're making is, in a sense, ChatGPT on its own is reconstituting what us humans have already written on the web and in books and things like that. It's putting it together in novel ways, but it's sort of the same pieces. It's not creating new knowledge. As soon as you have actual computation in the loop, and what I would talk about as irreducible computation, you can build what amounts to new knowledge. And so, yes, it surely is the case that, you ask ChatGPT plus Wolfram some question, it goes off, it creates a piece of Wolfram language code or something, it goes and runs somewhere, it finds new knowledge, it could then, if it wanted to, it could tweet that new knowledge, and then that new knowledge could get incorporated into the kind of, into the corpus of knowledge, the corpus of language that can be used by ChatGPT and so on. So yes, I think that the thing that is, the way to perhaps think about this is, in the end, there's sort of a whole separate civilization of the AIs that is in the process of developing. I mean, we already see that a whole bunch in the things that operate on the web today and so on. But I think we'll see an increasing amount of that going forward. And it's kind of, the way I've been curious thinking about so what's going to happen to all of us and when the civilization of the AIs is there, and what will it feel like to be in a world where a lot of what happens is happening in kind of the AI sphere and not in the human sphere. Already a lot of that is happening. I mean, already a lot of things that, we're presented with on the web and things like that come out of AI-like processes, not out of some kind of human decision making. But I think, the analogy is really our experience of the natural world. The natural world is full of what I think of as computational processes going on that are ones that we don't intrinsically understand. The natural world just does what it does. We have found a way to exist, to coexist with the natural world. We've had the convenient feature that we've had a few billion years of biological evolution to figure out how to do that. It's a little bit of a different situation with the kind of with AI, although we have the perhaps advantage that AIs are right now things which are created as a result of the things that the corpus of material that we've put on the web. I mean, I think the thing to understand about what's happening with computation and AI and so on is computation is a very broad kind of thing. You can, if you just pick a program at random, this is something I've been very much involved in over the decades actually, is asking, you take a very simple program like a cellular automaton program or a Turing machine for that matter, and you just say, I'm going to pick the rules for this thing, let's say at random, and they're tiny rules. Let's say just, 4 or 5 rules, 6 rules, whatever. And then you say, well, what does the system do? You might say, based on our experience with engineering and so on, oh, it won't do anything interesting and complicated because it's such a simple set of rules. That turns out not to be true. That's something I discovered in the 1980s. To my great surprise, it took me a number of years to kind of come to terms with that discovery, that even extremely simple rules are capable of generating extremely complicated behavior. That's a phenomenon of the computational universe that we're not particularly used to from our experience in engineering, because in engineering we want to do things where we can foresee the output. But so what happens is in the computational universe, there's immensely complex things that can be produced even with very simple programs. The question is, are those things that we humans, in a sense, care about? Are they things for which we humans would talk about in the usual things that we want to do? And so I think this idea of sort of creativity, computational creativity, yes, there's an infinite supply of computational creativity. The challenge is, of those things that are created, which are ones that we humans sort of care about? Which are ones where, in the development of our civilization, our natural language, things like this, we've actually got to the point where we think about those kinds of things. There are plenty of examples in history of, phenomena in physics where, who cared about liquid crystals until we realized that we could make displays out of them. Things like this. It's sort of what becomes something about which we humans kind of care. And this sort of, there's, as I say, an infinite supply of kind of computational creativity out there, which certainly is now accessible, for example, to ChatGPT. But if it goes off and starts running simple programs and produces all sorts of complicated output, people will say, well, that's nice, but it's until we get to the point where we have kind of a human narrative that kind of encompasses the kinds of things that are going on there, until we have a reason to care, it's just out there in the computational universe, not something pulled into kind of the human sphere.
I would love to explore this concept of creativity a little bit. I mean, first of all, reading your book was it was incredible. It opened up the whole world of emergence to me. And in a sense, you can think of a large language model as being a dynamical system, but it's sclerotic in the sense that it's been trained and now it's frozen. And something I was thinking about earlier was the irony that we almost never need to train it ever again, because now we can prompt it on how to use Wolfram and how to create these neurosymbolic architectures, and it's almost like we don't need to change it anymore. But then if you look at the representations it's learned and the way that our cognitive categories emerge over time, these are things that are baked into the language model, but the language models aren't very good at learning new things, at continual learning. And this kind of brings us to this semantic grammar thing. I just wondered what your thoughts were on the underlying model of the world that a semantic grammar assumes. Because when we're talking about cognitive categories, having it fixed isn't necessarily what we want.
Right. Interesting point. So, one of the things that, in a sense, I find, I'm just sort of coming to terms with it, is, in a sense, ChatGPT and large language models in general are, as you say, taking a snapshot of the world as we humans have created it, and they're just saying, okay, this is now the standard. Every essay should now be written this way because this is the average of what the world has produced so far. And it's kind of a funny time. It's sort of a standards moment for a lot of kinds of knowledge work and so on. And it's a little bit of a strange thing, because it's kind of, it now becomes, it's just like, in the past, there were probably no doubt, all sorts of creative ways, people might have written things by hand or done this or that. And then we have, the fixed idea of it's a font and everybody gets to, have the thing look the same way. So we've now done that for a large chunk of kind of knowledge work. And the question of sort of how we evolve, how we still keep doing new things, that's an interesting question. And I think that computation is the giant escape valve, so to speak, because it allows us to do huge numbers of new things. The issue is, does our understanding kind of follow along with the actual sort of ability of computation to kind of create the new, so to speak? And I think those are really interesting questions. I think the thing to understand kind of, if we think about the sort of computational universe of all possibilities, this is something, I've been, last few years, we've had these big breakthroughs that I didn't think would happen in my lifetime, but I'm really happy that they have, with thinking about fundamental physics in computational terms. And that's led to this kind of big idea of this thing we call the ruliad, which is kind of the entangled limit of all possible computations. Imagine you start all possible Turing machines with all possible initial tapes. You start them all off together, and you sort of simply look at what states those things produce. So there might be two Turing machines that produce different states, and then later on those states will converge because they'll end up being the same, and you get this kind of giant structure. And one of the things that's sort of a big result is we think that giant structure is kind of the thing that's underneath all of physics and all of mathematics, and kind of our experience of the physical world is we are embedded within this ruliad, and our experience of the physical world is taking some slice of that ruliad, experiencing kind of the set of all possible computations in a particular slice that corresponds to the ways that that our sensory data work and that our minds work. And I mean, just to say one sort of science point, the big result, I suppose, is that if you put only a small set of constraints on the way that we observe what's happening in the ruliad, actually really two constraints. One is that we are computationally bounded. We're limited in the computations we can do. The other constraint is we believe that we are persistent in time. Even though at every moment we get made from different atoms of space, we have the belief and the experience that that we persist through time. Those two constraints alone are enough to basically tell you that the slice of the ruliad that we observe will satisfy physics as we know it. In fact, specifically, the three big theories of 20th century physics, general relativity, the theory of gravity, quantum mechanics, and the statistical mechanics, the second law of thermodynamics, and so on. The amazing thing that's become clear from stuff we've done in the last couple of years is that all three of those kinds of features of physics as we experience it are a consequence of us being observers of the kind we are, observing this ruliad of all possible computational processes. So that's sort of a big picture version of sort of the physics side of things. But that leads one to this view that sort of minds experience the ruliad, experience this sort of entangled limit of all possible computations. It's like we are at a particular place in the ruliad, experiencing sort of the world in this particular way, just as we're at a particular place in physical space, experiencing the world with respect to that place in physical space. And so you think about sort of different minds as being different points at different points in the ruliad. So different human minds might be quite close in the ruliad, kind of the animals might be a bit further away, the AIs are somewhere in the ruliad. And what does it mean when we sort of make progress in making new paradigms about thinking about things? The way I see it is, it's kind of an expansion in rulial space. We are able to encompass more ways of thinking about the world than we could before. That's sort of the advance of paradigms, the increase of abstraction in fields like mathematics or science or whatever else. And we're sort of gradually expanding in rulial space, able to encompass more kinds of ways of looking at this kind of ultimate computational structure. So I think that this kind of the thing that we see as we the sort of the growth of our sort of the intellectual history of our civilization can be thought of as this kind of gradual colonization of rulial space. And and it's something that seems to happen quite gradually. It's not, you can easily just sort of pick a random program and jump to an arbitrary place in rulial space. The problem is that there won't be much human that you can say about it. It will be just, it's a program, it runs, it looks, but we don't have a way of kind of describing what's going on. I think that's sort of the limiting factor. And I think what will be interesting to see is, can we kind of go on expanding? Okay, we've got our large language models which are trained from the way the world is today. Can they tell us, oh, there's this new concept that's really worthwhile? Can we deduce from sort of the computational world and the world of large language models and so on, there's this obvious concept that you humans should be learning about. This is a direction that's worth going in. There's an analogy of this. I happen to have made a big study of the foundations of mathematics. In mathematics, it's very easy, given an axiom system for some area of mathematics, for example, to just enumerate all the possible theorems of easy in principle, at least, to enumerate all the possible theorems of, let's say, logic or geometry, or whatever else. You get this giant entangled limit of all these possible theorems. The question is, which ones have we humans chosen to actually talk about? There's sort of an infinite number of possible theorems, but there's only sort of an infinite space of possibilities, but only some places have we chosen to sort of colonize and describe. And so sort of you can think of the kind of the history of mathematics as being following these particular paths in kind of meta-mathematical space of all the possible things that one could be thinking about, all the possible theorems one could be considering. And so I think it's sort of this interesting thing in the world in general. What is it that we could be thinking about the world that we aren't thinking about right now? I'll give you an example. So fractal patterns, nested patterns, right? Things that we've known about, sort of popularized for the last 3 or 4 decades, and sort of known about for about 100 years. Well, actually, those kinds of nested patterns, so far as I know, were first invented by a mosaic layer in Italy in the 1200s, early 1200s. Made this thing, that particular person died, the art of making that particular nested pattern disappeared. The art historians wrote about many of the mosaics done by this family of mosaic layers. They never mentioned the nested patterns. They talked about the birds and lions and so on, but they were completely blind to this idea of nested patterns, which then in recent times, everybody who would see this pattern would say, oh, that's a fractal pattern. But this is the kind of example of how sort of when you have a new paradigm for thinking about things, you kind of notice things you didn't notice before. And a very interesting question is, what things are there in the world that we haven't noticed before? In my own life, the sort of the biggest one that was this phenomenon that I already mentioned about how simple programs can lead to extremely complicated behavior. That's a very fundamental scientific result that has all kinds of implications. But that's a result which, as I say, after I had first done computer experiments that plainly showed that result, it still took me several years to kind of realize, oh, that's a real thing. And when I look back, I realized there were zillions of examples of this that existed for hundreds of years, where people just ignored it. I mean,
I was wondering if I could jump in here, because what you're saying it's truly fascinating. It's the idea that these AIs could help us navigate this impossibly vast, space of possible computation, the ruliad. But there's also the other way around, which is us helping them navigate. And as you pointed out in this kind of wonderful essay back in February, what is GPT doing and why does it work? In this impossibly vast space, there's sort of total pure chance, there's complete randomness, and at this narrow boundary between, there's really chaos, which is where all the interesting stuff happens. It's where the irreducibly complex computations are. It's where Turing machines are. It's where all this rich behavior is, kind of on that boundary, and it's almost the sliver. And like you said, finding the programs in this vast space that are useful to humans or do something interesting is really difficult. And we've kind of been discovering over time that as you build systems that are more and more capable, they become harder and harder to train. And you talk about this a lot in your essay. And you're optimistic that we're going to find ways to train, these ever more capable systems effectively and efficiently. And I'm wondering how you think we're going to achieve that. Like, what's going to be the key to it? What avenues of research are promising to take us down that path of navigating the ruliad space?
Well, so first point to make is, this notion of computational irreducibility, which I think is really a pretty core notion that sort of we're starting to see kind of pop up in a lot of different places. It's an important piece of kind of intuition about science. The question is this: if you have a program, you have a set of rules, you know the set of rules, does that immediately tell you what the consequences of those rules will be? In traditional science, well, particularly mathematical science practiced sort of since the 1600s, kind of the big thing people are always excited about is science lets you predict stuff. Given that you know the equations, the rules by which something works, science will let you say, okay, this is what's going to happen sometime in the future. It's just once you know the rules, you can predict the future. That's been the kind of paradigmatic idea that people have about science for the last 300 years or so. what we realized from thinking about kind of computational universe, thinking about science based on programs rather than on equations, is that isn't always true. In fact, it's often not true. Instead, what can happen is you've got the rules, you run the rules, you can explicitly run them, you run them for 1 billion steps, you see what happens, but then you ask, can you jump ahead and say, oh, I know, can you figure out what's going to happen 1 billion steps in the future without having to explicitly run those steps? And the whole point is that you in general can't do that. And the reason you can't do that, well, there's a principle that I kind of came up with quite a long time ago now called the principle of computational equivalence, which gives you sort of an understanding of why you can't do that. The principle of computational equivalence says that as soon as you see a system which is not obviously simple in its behavior, it will tend to be equivalent in the sophistication of computations it can do. So, we've known since the 1920s, 1930s, that there are universal computers. There are systems that are capable of doing, that can be programmed to do any computation. What has not been obvious is that phenomenon and actually its generalization are quite ubiquitous. It's a thing that's been sort of interesting for me is you look at cellular automata, you look at Turing machines, you just start enumerating, let's say, possible Turing machines. The very smallest ones only do very simple things. As soon as you have a Turing machine with just, let's say, 3 colors on its tape and 2 states for its head, so 6 little cases in its rule, turns out the first Turing machine that doesn't do obviously simple things is computation universal. So that's kind of evidence for this principle of computational equivalence, that sort of as soon as the behavior is not obviously simple, it will be equivalent in its computational sophistication. So what does that mean? Well, when we're trying to predict something, we say we can predict it. What we mean is we, with our brain, with our mathematics, whatever else, we can jump ahead of it. It takes it 1 billion steps to figure out what it's going to do, but we have this clever way of just saying, oh, I know what you're going to do after 1 billion steps. The fact is, once we know about computational equivalence, we know that won't be possible in general. We know that there will be computational irreducibility. The only way to figure out what the system is going to do is effectively to follow through each step and see what happens. And that's sort of an important realization in science. It's an important sort of limitation of science coming from within science. It's kind of also a little bit the explanation for why bugs are hard to find and things like this. There are always sort of unexpected consequences. There are always things you couldn't readily foresee from the underlying rules that you had. But I think so this phenomenon of computational irreducibility, that's kind of that's hard computation. That's computation you can't reduce. In a sense, we should consider ourselves lucky that there is irreducible computation because, we lead our lives, we do all these different things. It would be really bad in a sense, one might feel it would be really bad if somebody could just say, okay, you don't need to lead your life. I know what the answer is. It's 42 or whatever else. There's nothing sort of achieved by the passage of time. What computational irreducibility tells one is that there's sort of something achieved by the passage of time, some sort of computational achievement from the passage of time. Now, now the question might be, well, how does that relate to things like training of neural nets and so on? Well, essentially, computational irreducibility is the enemy of neural net training. Because as soon as there is computational irreducibility, as soon as there's actually something you have to explicitly compute, you just can't do this approach of saying, well, training is about sort of knowing what will happen, being able to sort of explicitly burn in a prediction of what will happen. And that is explicitly that's sort of the opposite direction from computational irreducibility. So the thing that's exciting about, for example, our ChatGPT+WOLFRAM effort of today is that it's a place where we're combining something capable of doing irreducible computation with something that is sort of the interface to us humans. I mean, I kind of view sort of what ChatGPT is doing and a lot of its potential uses as being kind of a new form of user interface. It's kind of a linguistic user interface in the way that we've had in the past we had graphical user interfaces, etc. I mean, in a sense, Wolfram Alpha was, I think, the first sort of serious example of a linguistic user interface on the input side. We were not dealing with the output side. We're not writing essays. We're just generating essentially more like a GUI kind of output, a linguistic input, so to speak. But now we've got something where this is kind of humanizing kind of a lot of things by providing this kind of linguistic interface. And language seems to be our richest form of communication. And so having that linguistic interface is very important in having a richer form of communication with sort of the computational world. But I think this question of how do you find the things that are interesting to us humans? Well, that's something that I think these neural nets are beginning to actually know a lot about, because they just were trained on the things we humans produce. They, in a sense, have a very finely tuned sense of sort of what the current state of how we humans think about things is. And so if you say, well, what did we miss? That becomes a thing that it can potentially answer. The question of, and this is something I've been curious about, and I did some experiments, but they haven't been very successful yet, is kind of all possible, let's say, mathematical theorems, which ones are ones that a human is likely to consider interesting? We know some other ways to try and figure that out, but to be able to say, okay, large language model, you just learned all these things from what humans have cared about and put on the web. Now tell us which things exist in the computational universe, but we haven't yet sort of given names to, and so on. Which ones should we give names to?
Yes, I wholeheartedly agree that the gradient of interestingness is very important, but I also want to bring in the gradient of conceivability. Just before I do that, I wanted to comment on you referring to it as a linguistic interface, and I'm glad that you did, because it's an interface that can be used by many people in many different situations. But the key thing is that it's about being intelligible rather than being a conversational interface. But on this notion of conceivability, you said something fascinating, which is that there's this mosaic, and it was interesting to people, let's say hundreds or even thousands of years ago, and then it became lost. And Nagel's thought experiment about the bat is a subjective form of conceivability. And Noam Chomsky talks as a nativist about the domain of things which are conceivable as a function of the cognitive priors which are in our brains. So there's this trajectory space of things which are conceivable. And it's almost like we're cheating by creating these computational models which can, subject to irreducibility, can compute all of these different things. But the key question is whether or not we would recognize something as being interesting, or whether it would be conceivable even if it were present.
Right. So I think this is the thing. Progress is gradual and slow. In other words, if you jump to some random place in the ruliad, you pick a random program, you look at it, when you first look at it, it's like, I don't know why I care about this. It's something where we have to have a kind of I don't know whether you can call it cognitive or intellectual history kind of path that gets there. We don't get to talk about until we've built sort of the ambient ideas, until we built this kind of intellectual path, it doesn't really work to just jump to that place. It's like I could make up a word, and I don't know, I could make up a word for, I don't know, let's say look at clouds in the sky, and they have all kinds of weird different shapes. And we have a few names for a few of those shapes. Right now, we don't have a reason to care about the particular details of those shapes, but I can make up a word for one of those things. But until I can sort of tell you why we care about that, it becomes something that's very hard to. It's something we're sort of not connected to. I kind of think it's one of these things where it is there's sort of a sense of gradual progress, but you kind of can't. You can't kind of jump ahead. It's kind of like the computational irreducibility story, actually, that you can't kind of jump to a random place and expect to have understanding there.
Well, it may be the case too. Maybe we don't need to understand it, right? Because as long as, let's say, the AI is producing structured concepts, even if we don't understand those concepts, if they're structured enough that programs in Wolfram Alpha can make use of them to produce actions, let's say in the world, that are good for us, then we may not even need to understand those concepts, at least not yet.
Right.
I think
this is the kind of question of, once we define the goals, how those goals get implemented is something that is a matter of interest for science, but it's not necessarily a matter of relevance for the people using it. I mean, I think this is the thing which is sort of an interesting phenomenon in the history of computing particularly, is what is it that you're trying to get out of a computer? Well, you're trying to achieve certain goals. You're trying to, and this is where, my sort of lifelong story of kind of the programming languages versus the full-scale computational language idea. The programming languages which are really talking to computers in terms that computers intrinsically understand. Set this set up this array, and move this, do this loop, change this value from this to this to this. That's sort of the computer's intrinsic understanding. I think that the thing I've long been interested in is how do we go from something that is the way we think about things, how do we make a bridge between the way we think about things and what is possible computationally? And the thing that has been my long time effort is to build our computational language, Wolfram language, to be able to sort of be that bridge between the way we think about things, the things we think about, and what is computationally possible. So I think this question of sort of relating. Well, let's see. I think I didn't respond to what you were saying something interesting, and I think I lost my thread of what you were pointing out.
Well, it was really. I think what I'm trying to find out is what role human beings, are actually going to play in building the better architectures of tomorrow.
Right.
Because you made a point in that article from February that, right now, to be honest, the construction of these architectures is an art. It's really just people do some trial and error. They come up with some horseshoes or whatever shape, of architecture happens to work. GPT is in that, same kind of category. You point out there's no real science, behind that. And on the one hand, we could defer all that science to AIs potentially, and maybe we'll never understand the science that they do to build the next better versions of themselves. But I'm wondering if you also have any space in your vision for us developing human intelligible sciences that can do a better job of this. And if so, what might they look like, and what other sciences might they resemble? Zoology? I don't know.
Right. So I think the thing, so this question of this thing that's going on inside that's very complicated, that's computationally irreducible, what can we say about it? And we can still have something where there's complicated computations going on, they achieve goals we're interested in, we're happy, we're done. We can then go in, as you point out, and ask what's the science of what's happening inside. In a sense, the neuroscience has been that story of we know what we humans do. We know something about how the microscopic brain, works and neuron firings and so on. We don't have an intermediate language of neuroscience that is kind of the thing that is above the level of individual neuron firings and below the level of psychology, basically. And I think that's the question of can you find that and when can you find that is a very interesting question. I think one of the things that is a science point that when you have computational irreducibility, one of the necessary consequences of computational irreducibility is within a computationally irreducible system, there will always be an infinite number of specific little pieces of computational reducibility that you can find. In other words, even though you can't say everything, there are lots of little pieces, little things you can say. In a sense, that's why, if we take it at a more general level, if you say, well, what inventions can we make? Given the physical world, which has computational irreducibility, what things can we predict? What things can we invent which have foreseeable behavior, and so on? And the answer is there will be an infinite collection of these things. We'll never run out of inventions, little pieces of computational reducibility that we can find in this ultimately computational irreducible universe in which we live. So in a sense, we're always finding these little jumps, the little pieces of computational reducibility. And those pieces of computational reducibility may be big enough that we can kind of live in them. The fact that we believe space is continuous, that is a feature of a slice of computational reducibility from the underlying computational irreducibility of this complicated, the way we set it up with this, rewriting rules for some hypergraph that's going on underneath. That's a very complicated thing. If we were stuck experiencing the world in terms of this hypergraph being rewritten all the time, we wouldn't be able to sort of go and lead our lives in a simple way. It's like, when you have molecules in a gas bouncing around, if we had to follow every molecule, that would be a very different thing from our typical experience of a gas, which is just this sort of continuous fluid. So I think the thing that in we're kind of we experience, it's very important to find these sort of slices of computational reducibility, because they're the things that we can build engineering, we can make a predictable life out of, and so on. And those are things which, again, but many of those, many of those pieces of computational reducibility we haven't yet found, we don't yet have names for. As we find them, we may be able to make use of them, and we may be able to kind of expand our experience of the world in a way which makes use of those things. But I think is it the case that sort of we'll be able to use you're asking kind of, for example, one question you can ask is, will there be a science of machine learning? That would be a reasonable kind of question. Is it going to be the case? Right now people say, well, and what might a science of machine learning look like? Well, that's an interesting question. It's here's an example. So typically in machine learning, you do a training, you're finding a particular path where you get to a good point where you have a nice trained neural net. Imagine you followed all possible paths. It'd be a computationally absurd, thing to do, but the universe does something very much like that in the way that quantum mechanics works in physics. One of the things that's taken me a while to get used to is the idea that the universe is a profligate waster of computational resources. It's constantly following all these different paths of history, which we conflate together when we actually experience the world, but it followed all these different paths. So imagine that you did that for machine learning. Not necessarily practical at first, but imagine that you could do that. And imagine you could start thinking about kind of that space of possible paths that were followed. Imagine you could start using ideas from physics to think about that set of possible paths. Imagine you could think about things like, you could think about sort of the formation of something like continuum space out of all of those different possible paths that might be followed. There are ways that you could imagine doing some kind of science where you start saying, well, there's an event horizon that will form in this part of sort of training space, things like this. Now, right now, that might be something where we would say, oh, that's really quite interesting science. It's irrelevant to the practicalities of machine learning. Or it might turn out that understanding things at that level with that kind of sort of generalization and then going back to the specifics might turn out to be really valuable. I don't know yet. Mm-hmm. I think that what we can say from our experience in understanding physics and fundamental physics is there are some very powerful techniques that one can use that in a sense have already been discovered in physics, that once we know that physics is computational, they can be applied. Those things that have been discovered in physics can be transported to lots of other areas, like, for example, machine learning. But in terms of, do I expect that there will be many another thing to say about architectures of neural nets and so on is, the principle of computational equivalence kind of tells you in the end it doesn't really matter. In the end, if you kind of bash it hard enough, it's going to be able to sort of learn anything. Now, there may be, when I say bash it hard enough, there might be a factor of 1 billion difference in practice. And that makes big difference in the world as it is. But I think, and the other question is, the thing that we've been sort of lucky about is that, as I was mentioning before, the neural nets that we have, when they generalize in fairly human ways. And I think we don't fully understand that. I think that's a fact about neuroscience as much as it's a fact about machine learning. I don't think that's something, you can't prove that. It's not something where you can get a mathematical proof this thing is going to generalize in a human way, because it depends how we humans work. And that's something that is really a matter of natural science, of neuroscience and so on to determine. But, there happens to be an alignment there, possibly because the underlying sort of McCulloch-Pitts level architecture is quite similar between our brains and what happens in neural nets. And I think that's something that has been fortunate. I don't think, for me, I first looked at neural nets back in 1981 or 1980, and they didn't do anything interesting. I couldn't really get them to do anything. I decided they were way too complicated to understand scientifically, so I started looking at things like cellular automata, where you just have these fixed cells that have very simple behavior, and you don't have the sort of connection to everything else and all these weights and so on. And turned out that I managed to figure out a very rich set of behaviors that happen even in these much, much, much simpler systems. And those kinds of behaviors certainly will happen even more so in neural nets. Well, at least in the neural nets as they exist in something like ChatGPT are just essentially these feed-forward kind of networks that don't have the possibility of kind of having sort of infinite computations. They're just put in the input and let it ripple forward, so to speak. But
Yes.
But something in combination with Wolfram Alpha is what
Yes.
yeah, right. Well, once you can do that, once you've got sort of actual computation in the loop, and the thing that to emphasize perhaps about what I think we're adding to the world of kind of large language models with Wolfram Language and Wolfram Alpha is it's both the depth of computation, the kind of possibility of irreducible computation, and the structured knowledge of the world that we actually do have. There's a there, so to speak. There's an actual representation of, a city, a chemical element, a molecule, something like that. There's a hard computational representation of that. It's not, well, I saw that a few times on the web, and of course that's not how the neural net actually presents it, but it's sort of somewhere inside that neural net is some collection of weights. We don't understand exactly how, but is some collection of weights that represent the 100 times that this particular molecule showed up on the web. Of course, if you say, well, what about the molecule which didn't show up on the web? Well, the extrapolation from what did show up is an extrapolation based on this kind of extrapolation that neural nets do, that humans seem to also do, and whether that is what is the kind of scientific physical extrapolation, who's to say? The thing that has been one of the surprises was that neural nets and even large language models have been successful in things like protein folding, and it's a bit unclear. That's a place where that's really physics. That wasn't just us talking about things, or at least probably that's the case. I mean, in actuality, the way those things tend to work is they're sort of just making a correspondence with what's been physically observed to large chunks of the protein, and then the big effort of the machine learning model is to figure out how to fit together those sort of physically known chunks, so to speak, and how to sort of smooth out the correspondence between those. And it's sort of, I do kind of wonder the extent to which the there's the proteins there's the proteins that biology happens to use, which is a tiny set of all possible proteins, and sort of what the correspondence is between kind of what happens to get used in biology and what we happen to be thinking about and representing in human language. I think that's the when it comes to, you were mentioning the sort of the kind of what's interesting, so to speak, between
Yes.
the too random and the too simple and so on. And biology, I think, has also picked out some particular domain of things, and I've been actually a project that I started a depressingly long time ago when I was a kid, of trying to understand the second law of thermodynamics, which is this law of entropy increase, the fact
Right.
that things always tend to get more random. I finally sort of understood that, and I finally was writing something about it, and that's when ChatGPT came out, and I started to think a bit about that. But in any case, one of the things that's come out of that thinking about the second law is that we all know about solids, liquids, and gases, and so on. But when you have biological tissue, what is that? Is it a liquid? Is it a solid? Well, it's really neither of those things. It's a weird phase of matter that is kind of a computational phase of matter, where we increasingly know from molecular biology that biology sort of explicitly transports molecules around in sort of, quotes, meaningful ways. They don't just run around randomly. Not that they're really random in a liquid, but they seem random to us in a liquid. But we can already recognize that there is sort of structure in the way that things are transported around inside cells, inside molecular biological processes. And it's sort of interesting the extent to which even in the sort of that low level of biology, one's again seeing these things which somehow have this sort of they read to us as meaningful structure, and exactly how that sort of all fits together with what we can sort of how we understand what we can understand and so on. I don't know how that all works yet.
Thank you.
Wonderful. Dr. Wolfram, unfortunately, we've come to time. This has been an absolute honor. Thank you so much for joining us today. We really appreciate it.
Lots of interesting questions. We didn't get deeply technical, but this was really fun. Thank you very much.